Okay, here we go. This is AP Physics C. The goal here is to go through some of the problems. There were people who asked for me to solve some of the problems from the mechanics baseline, so here we go. So specifically they were looking for problems 15, 18, and 19. So in problem number 15 you had a pulley that was being accelerated by two masses of different mass. The one on the one side was M1 was 5 kilograms, M2 2 kilograms, and M of the pulley, so it has some inertia, is 2 kilograms. This pulley is a disc. We'll get into that, how the moment of inertia would affect that. So in this particular one, you're not going to see me write, you're just going to see me go through what the solutions that I would have and how I would write the equations and go from there. So the free body diagram of number 1 would just have the force due to gravity bigger than the force due to tension, because the mass 1 should accelerate it downward. So the tug of war should have the downward force being bigger than the upward force. And so I would write the equation, if you could see it, it's written over here, number 1, the sum of the forces over the mass. So A equals F net over M. You would take FG1 minus FT1 over M1 would give you that first equation. If you come over here and take a look at the free body diagram for number 2, it's going to accelerate up. Hopefully I've drawn this right, that the tension force has to be bigger than the force due to gravity. They look the same, but the tension force has to be bigger. And so I'd write an equation, A equals F net over M, the sum of the forces on 2 over the mass. So it would be the tension force minus the weight, because the tension force here, FT2, should win the tug of war, over the mass equals the acceleration. And then the other equation you're going to write is, because of the fact that this has some inertia, the sum of the torque, just like it was the sum of the force over mass, it's the sum of the torque over the moment of inertia equals the angular acceleration. And how is this going to be related? Well, the angular acceleration is the linear acceleration divided by the radius. So the sum of the torques, if you go over here and take a look at the free body diagram, at the point here where the string hits the side of each side of the pulley, the torque will be caused by that tension force pulling down on it on either side. So it's the radius, if you want to write the equation, it's R times FT1, that's the torque due to this force right over here, and R times FT2, which would be the torque caused by that one, over the moment of inertia, is going to give you the angular acceleration. So if you look at those, we may come back to those if we need to, but basically if you take a look at what we know, the moment of inertia is just 1/2 the mass of the pulley times r squared, and we're assuming it's a disc, so that's where we would get 1/2 mr squared. We essentially have 3 equations and 3 unknowns. Rewriting them, A equals Fg1 minus Ft1 over M1. The force due to gravity of Mg is M1 times G. The second one is A equals F2 minus Ft2 minus Fg2 over M1, and I've substituted here for Fg2 as M2G. And then the last equation, watch this carefully, if you look at it, it's alpha equals A over R, where R times the difference in the tension forces. And when we write alpha, remember that that's the sum of the torques over the moment of inertia, but then we're substituting 1/2 mr squared. If I bring this R to the other side, I get r squared on the top and the bottom. What that does for us is cancels out the r squared. So it really doesn't matter what the r is. So if you were thinking that you couldn't solve it because there wasn't enough information given, that's not quite right. In this particular case, the r's cancel. And what this is going to give us is an equation that says A equals Ft1 minus Ft2 over 1/2 the mass of the pulley. Okay. Now, still have a little bit of solution here because I have to solve these 3 equations, 3 unknowns, and If I solve the first equation for FT1, I get that. And I would advise you to either pause or do this on your own. I solved equation number 2 for FT2, and then I substituted in the next step for those into what I got for the third equation. A equals FT1 minus FT2 all over 1/2 MP, which is what this equation reduced to. A equals FT1 minus FT2 over 1/2 the mass of the pulley. So what I'm going to do is I'm going to combine like terms and solve for A. And so I've done some factorization. I get A times 1/2 MP plus M1 plus M2 equals G times the difference in the masses. And so the acceleration is one equation that has to do with the acceleration due to gravity and the difference in the mass over the total mass of the system. Hopefully that makes some sense, that would be, that you could look at it and maybe make some sense of that equation. The difference in the mass, or the difference in the weights, over the total mass of the system. Seems reasonable. If I do that and I plug in those, the difference in the weight divided by the weight forces divided by the total mass of the system, I get 2.178 meters per second squared. Then I can plug back into those two equations for FT1 and FT2, and I get that FT1 is plug in 5 times the acceleration due to gravity minus 5 times A, and I get 38.11 newtons for FT1. And the FT2 is 3 times 9.8 plus 3 times 2.178, and that's 35.93. So those are my three answers. A, 2.178, FT1, 38.11, and FT2, 35.93. So that's your solution. In a nutshell, long solution to problem number 15. Okay. All right. The next problem is this boom problem. So I've also written down the solution to that. You've got a situation where you have a rod and a weight, which we call a boom, supported by a tension in a wire. And they want to know what is the tension if you know that the mass of the rod is 5 kilograms and the mass of the boom is 12 kilograms. And the angle that the cord is with respect to the horizontal is 40 degrees. So you can see my free body diagram again in blue. The wall does push on this rod with a force in at an angle. There's some vertical component to it, and the force due to the wall, that's what the W stands for, in the X direction. But since there's no rotation occurring, the thing's in rotational equilibrium, the sum of the torques should be equal to 0 about the pivot point. And the pivot point would be the point over here, right there. So we're going to write an equation, remembering that torque is RF sine theta, or R cross F. The sum of the torques, well, the weight of the boom and the weight of the rod times whatever the lever arm is will give you the torque about that leverage point, pivot point. And then that's a clockwise torque, but the tension force is going to produce a counterclockwise torque. And you're only interested in the Y component because that has to be perpendicular to the lever arm to give it a measurable torque. So it's going to be the force due to gravity of the rod and the force due to gravity of the boom times whatever the distance is there, which would be the length of the rod divided by 2. And the torque due to the tension in the cord would be the Y component, Ft sine of 40 degrees times the length of the whole rod. So you can see that's where this equation comes from. Total weight of both of them netted together times the length over 2, because they're both being exerted right in the midpoint, minus the torque due to the other one, which is Ft sine 40 times L. So this minus that equals 0. I can do some math now and figure out the answer. I've got 12 kilograms plus 5 times 9.8, and I do have this factor of 2 divided by 2, equals Ft sine of 40. And so it's going to be the total mass times 9.8 over 2 times the sine of 40. And I get your answer of 129.6 newtons. So at any point you can pause, obviously, or go back to and look at it. Try to see if you can do the math and then maybe go back, either change the numbers or try it again and see whether that type of problem makes sense. We did do that in class with a demonstration, but it has been a while. So you might want to look at it again. And then the last problem that people were interested in was this number 19, where you drop a ball. By the time right before it hits the ground, it has a velocity of 12 meters per second. And afterward, it comes back up to a height of 4 meters. And you want to find out what is the speed right after the collision with the ground, and what is the percentage of the kinetic energy lost in that collision. So I just did some straight total energy conservation. E equals E prime. The total mechanical energy would be the potential energy due to gravity plus the kinetic on both sides of the equation. E equals E prime. So the kinetic energy right before it hits the ground is going to equal the change in potential energy plus the kinetic energy at the top. But at the top it should be 0 because it's reached its highest value. So the kinetic energy at the bottom should equal the change in potential energy to get back up to the new height. So 1/2 mv squared is mg delta h. This is nothing new. So the velocity right after it hits the ground is going to equal the 2 times 9.8 times the height, which is the 4 meters. And if you do the math, you get 8.854 meters per second. So this is after the collision with the ground, just doing energy conservation from here to there. So the velocity that immediately leaves the ground would be 8.854. And so the last step would be to figure out what kind of energy change was there. The kinetic energy right before it hits the ground would just be 1/2 mv squared. And so if you do that, notice the mass was 1. 1/2 times 1 times 12 squared, you get 72 joules of kinetic energy. The kinetic energy after would just be 1/2 mv squared, and you put in 1/2 times 1 kilogram times 8.854 squared. And that turns out to be 39.2 joules. So if you want to know what is the percentage lost, you might want to find out, well, what is the percentage of kinetic energy you have left? And if you divide the two numbers, you get 54.4%. So if you just subtract from 100, you lost 45.6% of the kinetic energy in that problem. Okay, so those are the 3 problems that people emailed that they wanted to see once again. So hopefully this was useful. So let me know if you have any other questions about the mechanics baseline. Otherwise, have a good day. Stay safe.